with molecules that have multiple central atoms and get you to appreciate the complexity that can occur in those types of situations. So we want to consider what happens when we have more than one central atom in a particular molecule, and so we have to consider the atoms that are not terminal but are on the inside of molecules. We're going to use the same basic rules that we've been using. So in our example here, we have a molecule that is of biological interest, glycine. It's one of these relatively simple amino acids. In this particular case, you see the Lewis dot structure shown on the bottom of the slide. In this case, we have multiple central atoms. In the case of the nitrogen atom, we have 4 electron regions, 3 of them being bonding regions, 2 between the nitrogen and hydrogen atoms, and 1 nitrogen carbon bond, and then also a lone pair. The additional then situation is we would describe the molecular shape of the nitrogen atom in terms of the 3 bonding and 1 lone pair geometry that we would describe as being a trigonal pyramidal type structure. So that particular atom is trigonal pyramidal. The carbon next to it has 4 bonding regions, 2 carbon-hydrogen bonds, 1 carbon-nitrogen bond, and then also a carbon-carbon bond. So again, in this particular case, we have a tetrahedral molecular shape. There may be slight distortions because of the different sizes of the atoms involved, but we describe that carbon atom as being a molecular shape of tetrahedral. The carbon next to that has 3 electron regions. In this case, we have a carbon-carbon bond, we have a carbon-oxygen bond, and a carbon-oxygen double bond. So in this case, we would predict an electron geometry of a trigonal planar structure where the angles are 120 degrees. And so we would describe the molecular shape as trigonal planar for that atom. And then finally, we have an oxygen atom next to that, which has 4 electron regions. There is a carbon-oxygen bond, a oxygen-hydrogen bond, and then 2 lone pairs. So in this case, then we would say that the molecular shape is bent, with an angle being approximately 109.5 degrees, maybe slightly less than that due to the distortions created by the lone pairs on that oxygen. So in order to represent the 3-dimensional shape of this particular molecule, there are a number of possible orientations that can occur, but ultimately the molecule will adopt a shape that then looks for the lowest possible energy situation. And so we can represent these shapes instead of drawing them in a 2-dimensional arrangement on a piece of paper. We would need to have some sort of way to interact or indicate that certain atoms are coming in and out of the plane of the page. And so in this case, as you see down on the bottom here, the bonds that are coming closer to you are represented by wedges, and the bonds where the atoms are going back into the page are represented as dashes. And so this is a fairly reasonable approximation of what the shape on average of glycine would look like. So we can also represent this in a ball and stick model. Allows you to see a little bit better how much room each of the atoms takes up around the central atoms. At this point, we need to revisit the concept of dipole moments and the fact that various molecules can have polar covalent bonds. A dipole moment is a result of an unequal distribution of electron density within a molecule, often because of differences in electronegativity between two atoms that share pairs of electrons. The example shown here is hydrogen fluoride. Fluorine being much more electronegative than hydrogen, those shared pairs of electrons spend more time closer to the fluorine, so hence we describe this as a polar covalent bond. And the vector arrow that you see here indicates the direction associated with the molecular dipole in this case. It's a relatively simple molecule because there are only two atoms in the formula. But we can have situations where there are more than two atoms, and then at this point we have to consider the symmetry associated with the polar covalent bonds. So a good example of this is carbon dioxide. In carbon dioxide we have two different carbon-oxygen bonds. The oxygen atoms are quite a bit more electronegative than the carbon, and so we would have a situation where there are two different polar covalent bonds in this molecule. This creates a situation where there are partial negative charges on the oxygens and an equal amount of partial positive charge on the carbon. So these are clearly polar covalent bonds. The problem is that we have the vector arrow for one of those bonds that is pointed to the left, whereas the other one is pointed to the right. And they're exactly the same magnitude or size in terms of the dipole moment for those bonds. So this situation results in a canceling of the overall dipole for the entire molecule. And so since the vectors are in opposite directions and there's a molecular geometry with an OCO angle of 180 degrees, this molecule ends up not having a dipole moment, even though it does have polar covalent bonds. In this example, we have a water molecule, H2O, and so we want to consider whether or not this molecule has a dipole moment. In this case, oxygen is more electronegative than the hydrogen, so therefore there is a polar covalent bond where the electrons that are shared are pulled closer to the oxygen than to the hydrogen, so the hydrogen becomes slightly positive, whereas the oxygen becomes slightly negative as a result of that. There also is a second OH bond, which is also polar covalent. In this particular case, the angle of the HOH angle is not 180 degrees, it's closer to 109.5. It's actually slightly smaller than that because of the presence of lone pairs. So in this case then, we have to ask ourselves, does the vectors, or do the vectors result in a net dipole moment when we add this all together? So we have to do a little bit of vector addition in this particular case. So what you can do is end up drawing a vector triangle where the red vector that we have shown for both of the bonds is actually broken up into two components. One of them is vertical, the other is horizontal, forming a right triangle. You'll notice that the two horizontal components are pointed exactly opposite directions, and those two vectors are going to cancel one another, end up forming no net dipole in the horizontal direction. However, you'll notice that the two that are in the vertical direction are both pointing in the same direction. So when those two are added together, they produce a net dipole moment that is in the vertical direction, with the negative end of the molecule being on the oxygen, and so therefore we end up with a new vector as shown here that basically bisects the HOH angle, and therefore our conclusion is that this is a polar molecule and would have a dipole moment. So the lone pairs in this particular case are representing the electron density and the direction of this dipole moment. So when we actually measure the dipole moment for a water molecule, it is not zero. It has a value of 1.94 debye.